Okay, so we're going to start a new topic, and this is class 21. We're going to talk about internal flow, and by which we mean usually flow within pipes. And in our textbook, I do believe this is going to be chapter 8. And so in this first part today, we're going to talk about laminar turbulent flow in pipes and talk about major losses. And in the next class, we're going to talk about minor losses, and we're going to implement that to do a piping system pressure drop analysis. So we've touched on these a little bit in our treatment of Bernoulli, and when we added losses, when we used momentum and I think momentum. No, we used energy. Yeah, Reynolds transport theorem. We applied it to energy, and we had Bernoulli, and then we add losses and pumps and so forth. But this is going to be more detail. All right, so the big idea is we could have a laminar and turbulent flow. So laminar is, you could think of it as being slow and sticky, whereas turbulent is fast and chaotic. Where on laminar is really viscous forces dominate, and in turbulent it's really inertial forces dominate. So I guess I just put this in here to mention, I guess in the next class, really, where we're going to talk a little bit, or just allude a little bit to this method of finding flow in losses in pipes is called the Darcy-Weisbach, sure, why not Weisbach method. And it's cataloged in this Crane, which is a valve company, a document called Flow of Fluids, technical paper 410. So it's an interesting thing that this is a pretty good book, covers in a lot more detail on how to do pressure drop analysis. All right, so internal flow here, chapter 8. Our goal is to find a relationship between flow and pressure drops in conduits. All right, so we might even include ducts as well as pipes. But as opposed to civil engineers, they actually will look at, and of course, maybe my audiences might be some civil engineers, but they often will look at partially filled conduits. We're having completely filled conduits that we're looking at. And what you're seeing here is we could inject like some dye into the inlet of some pipe, and we could track that dye, and you can kind of see what it looks like, and that might be a good visual for what the laminar versus the turbulent might look like. And we can even have sort of like this translational or transitional, I should say. So it's already written down in that slide, but things that I would say that we would want to take a look at is that the Reynolds number in this case. Usually we'll be talking about density, velocity, diameter, and this is the pipe diameter and mu. Notably that you could also simplify this by velocity times diameter and go mu, because the definition of this kinematic viscosity is it's the dynamic viscosity divided by the density. But in either case, remember that this stuff on top is really sort of like inertial forces, and the stuff on the bottom is more like viscous forces. So as with many of the non-dimensional numbers, they can be thought of as like a type of force ratio. The numbers when dealing with pipes, we'll have, in other applications, there will be some dividing line for Reynolds number between what's turbulent and laminar. But it's going to, these values that we're looking at here are specific to being for pipe flow. And Reynolds number that's greater than 4,000 is considered turbulent, and a Reynolds number that is, let's say, less than 2,100, I don't know why they don't just say 2,000, but that's fine, is considered laminar. And then something in between is what might be considered transitional, right? So it's sort of like not quite one or the other. When fluid enters into, say, a pipe, it goes through sort of this unsteady region right here, where it's making, it's kind of deciding what it's going to be. Like it has like sort of a uniform flow velocity, but we know that the viscosity is going to create, we anticipate it's going to create this velocity profile that looks like this because of the no slip condition. So there's this like transitional type of thing. And if you wanted to find like what the length of that is, this is an LE right here. There's a formula to find how long it takes, what the length it is, that is the LE it is to take to get this entrance length, and it's 0.06 times the Reynolds number. It has been found that it would take if you multiply that by d, and it really gives sort of like the number of diameters in terms of a length that it would take before you would have a nice and consistent steady flow. So it's actually unsteady for this entrance length. And then we have what we call fully developed flow until it comes into something that's going to disrupt the flow. And one thing that might disrupt the flow could be a bend, right? It could be all kinds of things will disrupt the flow, but a bend will, for one thing, because the velocity is about to change, right? So the inside velocity is going to be somewhat slower than the outside velocity, and that causes some amount of unsteadiness to there until there's enough pipe length to go through. So once again, we have a region right here that's unsteady. So this up to this point right here is going to be steady flow in that region. And then once it's gone through enough pipe again, it will become steady again. Now that doesn't necessarily mean that it's going to be turbulent in these spots, although it can, right? This can trip the thing and cause vortices to include, and that's really a lot of what the unsteady thing is those vortices. So there can be some amount of turbulence in here, but it's just the idea that there is not a consistent velocity profile, and that's what makes it unsteady. The entrance length, however, but it can be turbulent and still have a fully developed flow, right? But the flow, the velocity profile, I should draw that somewhere. The velocity profile in a turbulent won't be as parabolic. It'll be like high, and then it can actually kind of be flat, and then like this right there. So, and I just didn't make the thing symmetric, but it should be symmetric. And by the way, this is, of course, this is round, right? So just you have to kind of picture that in kind of in three-dimensional. And didn't do much of a better job right there, but like you could see that this is right, the boundary layer that you could kind of think of in terms of or similar to the boundary layer right in there, and it's almost like a uniform region of flow. And you wouldn't think that for turbulent, right? But you can say that, like, well, we sort of have this uniform flow kind of region in the center of this piece. But just to complete the thought here, that entrance length for a turbulent flow can be found from 4.4 times the Reynolds number raised to the 1/6. And so you could kind of like get sort of an idea that there's this dependency on the Reynolds number to find how many how many diameters it would take to get it steady. This is really sort of a useful kind of a parameter in some respects, because there are certain applications, including flow meters, and I don't mean the kind of flow meters that we were looking at, but actually, those flow meters too need to have a certain amount of distance without bends or valves or fittings or anything, so that they aren't influenced by the unsteady nature of the flow in front of and after a flow meter. So it's not a this is not a useless piece of information. The big idea in all of this flow, all the internal conduits, is there's always going to be a pressure drop. And that pressure drop, though, is the total pressure. It will drop. And it's going to drop because of shear stress, between pressure and shear stress. And we'll see here in a second where we can do a short derivation. Now, if it changes, the area, the diameter changes, the velocity might increase, and the static pressure, the pressure that shows up on the gauge, that can increase. But inevitably, the total pressure, which is the combination of static pressure, hydrostatic pressure, and dynamic pressure, what's on the left hand or the right hand side of Bernoulli, will always drop because of losses. So it drops as they go along. And you could think of the pressure drop in two ways, right? One is due to shear forces must overcome pressure differences. Must be overcome by pressure must be overcome. Sorry, the shear forces have to be overcome by the pressure differences. So there's got to be a high pressure over here compared to here, and there must be some type of pressure difference drop from here to there, because there's shear forces that are trying to stop right there, right? Or you could think of it as being viscous energy viscous energy losses, and that they use up the pressure differences, right? So you could think of it in terms the pressure. We get the pressure energy. You can think of energy differences. So that's the reason why the pressure is always going to drop as you move along. All right, I'm taking way too long to say this and stuttering and stammering, but we'll get through it. Right? It's supposed to be my rehearsal anyway. All right, so everything on this page, you should remember, is going to be for laminar flow only. And I wrote a warning that any equations that we might show up on this page aren't to be used for anything except something that's below 2100. Well, right here's a nice little FBD that we could use to kind of quantify what this pressure drop is like, right? So if we take the sum of the forces in the x direction, and we'll note that we have a pressure on this face and we have a pressure drop on this face, right? So this is a force right here. Here's the pressure on the front side, and here's the pressure on the back side with the original minus whatever the delta P was going to be. We also have the shear of the wall that's acting on all sides of this. So if we take a balance along this thing, and by the way, this is going to be over length of L right here, we will have P1 times pi r squared minus P1 minus delta P times pi r squared, and then the area around this outside is really the circumference times the length for here, and that's also in the negative, and we're going to have tau. That doesn't look like a tau, but that's tau. It's tau times area is going to be the force, and that area is 2 pi r, that's the circumference, times the length, and that gives us this outside area. It's going to be equal to 0. So we're going to go ahead and see that this guy is getting canceled out right there. So we'll also see that right here we're going to get rid of one of the radii, and we're going to get rid of the pi. And what we're left with here, we're going to divide delta P, because we often want to care about what the pressure is dropping per length of the thing. It's going to be equal to 2 tau over R. Now, we know something about tau already, that tau can be defined as being mu times du d height. But in this case, we're going to use the radius, right? And so do things on a per radius basis, and maybe I could draw my axis, like here's the x direction, and here's my r direction, right? And also that this thing right here, use capital R to define the actual radius, right? So here's the variable and here's a constant. This R is the radius of the inside of the pipe. So this is going to be dr right there. And in any way that you do this right here, remember that this is going to be the slope of the velocity profile. And in this arrangement right here, it's actually negative, right? So no matter how you slice it right in there, we're getting a negative slope that's taking place. So we can substitute this tau into here. Notably, this is on an r basis. We have an r here. We're going to do some integration is what we're going to do. And so we can rearrange this so that its du is going to be equal to negative 1 over 2 mu, right? We just brought them over to the side, times delta P over L, and then r dr, right? And we can integrate from no slip condition to the center, right? So we're actually going to go, we might start actually in the middle right here and go outwards. So we might actually, I don't know, we might go from a V center of the thing, this VC in the center, to the 0 right in there. Just be aware. And then we're going to integrate this one. Let's see, we could actually put the integral, all these are constants. Well, they'll eventually be a constant once we know what that pressure is, but we can go from 0 to big R right in there. And what we end up finding is we could find this as a function VC, right? And that VC is what we're going to say that's going to be the center of the thing. And 1 minus R over capital R squared. And what that describes is this profile with a magnitude of VC, and I probably shouldn't have put this as VC. Should probably just keep this as U, because we want this U as a function of here. But we can say that VC, and we can go where VC, the velocity at the center, is going to be delta P. There's going to be an L on the denominator, but I'm going to keep it over here to the way we're writing it. And 16 mu times L. Oops, I'm sorry. And it's noted here that in an ideal inviscid profile, we have this right here in the Laminar, but we're going to say that the velocity, the average velocity, would actually be this VC divided by 2. So if you want to have the average velocity, it's going to be equal to delta P d squared over 32 mu L. It's already extended past the time I usually give for a video, but I'm going to keep going because I want to just complete the laminar stuff right here. We might have equations or we might have occasion to include the angle. You know, I think I'm going to go ahead and bypass this because I don't think it's necessary or useful to us. But what I do want to say, so I'm going to go ahead and say that we're going to skip this. I think I'll skip it in class too. So we're going to skip this. We could take care of this whole thing with Bernoulli, this part of it right here. So just be aware. So it's not necessary. But what we can say up above right here, we have two equations. We could rewrite this equation up above and notably say that we know that the area, or well, we know that the area is going to be pi over 4 d squared, and that if we were going to want to find the flow, we would take the velocity, the average velocity, and multiply it by the area, right? So in doing that, we could take this equation and find delta P times, well, I think we're going to need a pi in there. Let me put it in the order that I have it. Pi times delta P times the diameter fourthed divided by, comes up to 128, because you're going to have 4 times the 32. And then you're going to have on the bottom mu and L. Or you could find the pressure drop by rewriting all of this as being 128 times mu times L times this flow divided by pi divided by d4. So what we've done is we have made a relationship. Our goal, as we stated at the beginning, was to find a relationship between pressure drop and flow. Find a relationship between flow and pressure drop, and that's what we did. But we have to make a warning, only for laminar flow. Which means that these can only be used for equations that are below Reynolds number of 2100. So I'm going to go to the next slide here, and we're going to talk about turbulent, and we're going to introduce something called the Moody diagram and the Darcy friction factor. So that's going to be exciting, and I know you're looking forward to it.